Hi, welcome to Earth Science. Uh, we're going to be doing chapter 6 today, which is talking about metamorphic rocks. I'm doing something a little bit differently at the end of this chapter, so make sure that you look at the questions at the end. I'm going to give you some helpful hints to answer some of these questions. So if you're watching this, make sure you don't end early. So when we start looking at metamorphic rocks, you'll recall that we talked about these in the rock cycle earlier on, but metamorphic rocks are the third and final type of rock that we've covered for the last two chapters. We've talked about igneous rocks formed from magma or lava, sedimentary rocks formed from sediment or a solution. And the third type of rock is a metamorphic rock, which we take an existing rock, we undergo some type of solid state change in order to make a new rock. Now, when I say solid state, it means that we have not changed into a liquid, because then we'd be either in a solution of water or back into a magma. And so when we start looking at metamorphic rocks, these are rocks that have undergone some type of steady state change. So to really understand these rocks, these tell a lot of stories. Not only do they say what the rock is, but what temperature and pressure created this new rock. So not only do we understand kind of the history of this rock, but also what caused these rocks to form in this way. And so an example would be a shale turning into a garnet schist. And we've got some examples of these later on this chapter. So there's a number of different ways that we can take a rock and turn it into a new rock. We can partly change the rock, as the name implies. Meta means partly, morph means to change. So we can take a rock into a different rock. And I would encourage you to go through the videolets that are in the student user guide for the web page, because they have some really good animations that are looking at these different types of processes. So the first one is recrystallization. Recrystallization is where you take grains of minerals. Remember, a mineral is a crystal. That then you can take these minerals and make them into larger minerals without changing the identity of those minerals. So you can take examples here. We have the original material was a sandstone, and you can see in the image here that the grains are really tiny, small grains of quartz. And under the right temperature and pressure conditions, we can take the protolith, the original rock, and turn it into a larger metamorphic rock, a larger grained metamorphic rock, and we'd call this quartzite. The next type is where we can use a phase change. And in a phase change, you're going to use the same chemical composition, but different crystalline structure. The classic example of this is when you take a graphite, which we learned is the made up of carbon, but its lattice work has really big spacing, kind of like chicken wire that's been with large spaces in between. And then if we squeeze this mineral together, we can actually change the crystalline shape and make a mineral called a diamond. And another way that we can make a metamorphic rock is through metamorphic reactions, where atoms are separating from one mineral and rebonding to form a different mineral. And so the example of this would be clay minerals and quartz turning into the minerals garnet, mica, and also making additional quartz. And silicon and oxygen are so common in the continental crust. Finding quartz in lots of different locations is not uncommon. One of the ways that we can do this is another way we can form metamorphic rocks is by squeezing these minerals. And in this case, we have the protolith has spheroidal grains, otherwise rounded grains. But if we squeeze these grains, what's going to happen is the minerals will get elongated, and we'll lose the minerals that are under greater pressure because of this squeezing. And so the ended result would be elliptical grains. Another way, in addition to pressure solution, and this is using the pressure, is through plastic deformation. Now, this is where the minerals themselves are not being destroyed and reapplied in a different location, but they're being stretched out and or smushed. Plastic means to bend it and it will keep its shape. And so if we start looking at a mineral that undergoes plastic deformation, a spheroidal grain would become elliptical by this just sheer squeezing of the grains. And in this case, the grains themselves are being squeezed. If we take a look at the pressure solution, the grains are being destroyed in one location and regrowth in a different location. So I would encourage you to look at these different animations in the user site on the Norton web page. They're also linked in the PowerPoint presentation. They just didn't come up very well when I was trying them on Zoom. So what are the major agents of metamorphism? The first one is a change in pressure. We know that, well, a change in temperature, actually. A change in temperature is a measurement of how fast these grains are moving around, and the higher the temperature, the faster they're moving around. Another change that we can have is a change in pressure. And as it turns out, these are both intricately related. You may recall in a physics class, you may have talked about the ideal gas law, where temperature and pressure are intricately related. We're going to see that again today in metamorphic rocks. So an increase in temperature is going to cause these rocks, the minerals, to potentially break off one of the bonds as a result of these atoms vibrating faster and recrystallizing in a different location. It is not causing it to melt, but it just moves the mineral grain from the atoms in a mineral grain from one spot to another. And temperature, if we go deeper into the earth, the temperature does increase. We can also increase the pressure. And the difference with temperature is that the pressure is going to be squeezing down. The deeper you go, the increase in pressure in all directions. And so this isn't going to cause an elongation of minerals, but the pressure is just going to be greater in all directions. Think about going down to the bottom of a swimming pool or a lake. The deeper you go, the pressure is not just pushing down on top of you, but it's in all directions. That water pressure. Well, rocks experience rock pressure. This is quite dangerous if you're going into doing some mining, because the deeper you go, those rocks are used to being under the pressure. So if they're under that pressure and now you're causing them to experience atmospheric pressure, you're digging a hole in that area, releasing that pressure, this can cause mine collapse. So we want to be very careful when we start putting in deeper mines because of this rock pressure. Water is really, really important, and it can't be understated enough how much water plays a role in metamorphism. One of the ways that water plays a role in metamorphism is that it allows very hot water solutions to speed up the metamorphic process. If you look at this water molecule, it has a positive side on the hydrogen side of a water molecule and a negative side on the oxygen side of the water molecule. And so as a result, water can attract any type of any mineral that has a positive or a negative charge, or ion that has a positive or a negative charge. It's for this reason we call water the universal solvent, because it can take positive or negative ions depending on what side of the water you're looking at, and it can move this water, since it's a fluid, it can move from one location to the next. And so we call this chemical compositional change as a result of this water moving from one place to the other as metasomatism. And that just means that these minerals are moving from these ions are moving from one area to the next. And as a result, you're going to end up with different minerals as a result of these fluid movement in this rock. Now, the application of stress, there's different types of stress. So let's take a look at the 3 different types of stress. The first one that I've mentioned so far is compressive stress, where the rock is getting squeezed. And if we go deeper into the earth, the rock is squeezed in all directions. And so we have unilateral or isometric compressional stress. Then we also have tensional stress. This is where rocks are getting pulled apart. And then we have shear stress, where we apply this pressure in different directions. The shear angle is a force that moves material along or sideways relative to one another. And as it turns out, all 3 of these forces can occur in metamorphic rocks. We can get tensile stress, we can get compressional stress, and shear stress. And so if we have the pressure in the same in all directions, what's going to end up with is those rocks are going to be under, we're going to end up with unilateral pressure. But many times what we have is what's called differential stress, where we end up with more pressure in one direction than in the other. And so the result of a compressional stress can in fact cause minerals to become elongated. And we can actually see which direction a mineral has been smashed. And so in this case, these minerals, how well this is showing up in the color in the photo, but we can actually see that this mineral has been smashed in this direction. A foliated metamorphic rock is a rock that exhibits this differential preferred orientation. And so my classic example of this differentiated stress would be particle board or plywood, where you can actually see which direction those minerals are aligned, or which direction they got squeezed, those wood fibers, in order to make this synthetic metamorphic style rock. Some examples in nature, we have things like slate, phyllite, schist, and gneiss, all of which have a preferred orientation. They sometimes might have a striped appearance, and we'll look in the lab at some examples of this. If not, your book does have some great examples of these images of slate, phyllite, and schist. In fact, if we look on page 176, we can see some of those examples, and 177. Non-foliated rocks found on page 178 don't have a differential direction alignment to these minerals, and so we call this non-foliated. A non-foliated rock does not contain metamorphic foliation. That we call this directional metamorphism foliation. And some examples of this are things like quartzite, marble, and hornfels. You may be familiar with marble. Marble is made from limestone that's been baked, and as a result, there's no real preferred break. And you'll recall limestone and marble are both made of the mineral calcite. Calcite is used in statues because of its low hardness. It's only 3 on Mohs hardness. So you could easily take a piece of marble and you could sculpt it into various shapes. So let's look at some examples of these metamorphic rocks. The first one of a foliated metamorphic rock is a slate. And a slate is formed when you take a shale or a mudstone. A shale or a mudstone, and if you recall, these little clay particles represented by my poker chips are bits of clay particles that kind of just align there, and maybe we get some little fusing at where the grains are coming together. But if we started to squeeze this together, we'd get rid of some of the pore spaces, and if we get rid of these pore spaces, these clay particles would line up and become much more flat. As a result, they break into flat sheets. These flat sheets make excellent roofing materials, and so you could actually use these slates for roofing. Additionally, you could use the slate for floor tile pool tables. So the wood, if you had a wood pool table, it would sag, but slate holds its shape quite nicely. Also makes pool tables really heavy. We could also use it for a blackboard. And in the past, we used slate for blackboards. If we apply a little bit more heat and pressure, what is going to happen atom by atom is these mineral grains are going to get a little bit larger. And as they get a little bit larger, what's going to happen, instead of being in these nice lines, what's going to happen is they're going to start to buckle up a little bit. You're going to tend to form some minerals called mica, which you may have already identified in our labs. It was that one that kind of looked like plastic, that muscovite mica. What's notable about micas is they all break into flat silicate sheets, and they reflect light. I think I mentioned that they were used in makeup. And so these micas are going to reflect light. Now they're going to be microscopic. You're not going to see the individual grains, but you'll see that they are in fact flat, and that these minerals are going to start to create this wavy or buckled up appearance, and it's going to reflect light as a result of those little micas. If you increase the pressure a little bit more, you're going to get larger grains, and we call this sample that has large enough grains that you can see the individual samples a schist. Now, some cases, some different minerals are going to be formed. Here's an example of one of those garnet schists, where you have these large garnet crystals in this schist. In this case, I have a mica schist, where you end up with larger grains of muscovite mica. And then finally, the last form of metamorphic rocks are going to cause the light-colored minerals to start to segregate from the dark-colored minerals, and you end up with a gneissic texture, where you end up with light and dark bands of these minerals. And nature doesn't like to be put in a box. If you started to melt this material, or almost melt this material, there's actually a transition between the gneissic textures and the igneous blob of magma, which would cool to form an igneous rock, which we've already covered, and it's called a migmatite. So it's kind of an in-between between metamorphic rocks and igneous rocks. So some of the other famous non-foliated metamorphic rocks. So again, non-foliated means not having that smushed over appearance. And the classic example that I like to give when looking at a non-foliated metamorphic rock is pottery or bricks. In either case, you would take clay and you'd fire it in the oven. And as a result, what's going to happen is the grains are going to enlarge, and you're going to end up with a little bit larger crystals, which are going to be, again, a little bit darker, a little bit more compressed. And so if we had a sandstone, grains of material that are all bits of quartz grains, and so you can see those individual little grains. But if we start baking this material, or we start adding enough pressure that we're going to cause these pore spaces to become non-existent in larger quartz grains, what you're going to end up with is a sample that's called quartzite, a metamorphic rock. Now, no matter which way you move this metamorphic rock of quartzite, it doesn't really have a preferred break. It doesn't have that foliated texture. And I've already mentioned, if we had a bit of limestone, as indicated on the left there, you can actually, in some cases, see, oh, there's little tiny fossils. Since marble or limestone is made up of the mineral calcite, and we can have these biocalcite minerals. If we start baking these minerals, what is going to happen is those original fabric of the limestone is destroyed, and what you're going to be left with are just calcite crystals as indicated on the image on the right. Again, calcite is an excellent sample for carving because of its low hardness, 3 on Mohs hardness scale. The downside is both of these samples are easy to dissolve. And so if you're making a headstone out of this marble, the downside is it could wash away, it could chemically weather quite quickly. So when we start looking at metamorphism, we want to look at something called metamorphic grade. Since temperature and pressure both work together to change these minerals, or partly change these minerals, or metamorphose these minerals, if we start looking at the minerals, we can actually work backwards and figure out what the temperature or pressure is. Now, in some cases, we can't really tell, was it a low pressure, higher temperature, or high pressure, lower temperature? We're going to lump those things together and call it the metamorphic grade. And so when we start looking at this chart here, if we started looking at these different different metamorphic rocks, we have minerals like blue schist, which is a schist that has this bluish appearance, but it's going to form under high pressure, lower temperature. Where if we took that exact same that sample and we would increase the temperature, we'd actually start to break down these minerals at that same temperature, by the same pressure. And so when we start looking at some of these different metamorphic grades, again, the combination of low pressure and low temperature is a low grade, high pressure and high temperature is a high grade, and then we've got this intermediate where you're increasing one of those two parameters. We get these different minerals. And so if we take a look at these metamorphic rocks, we can get a clue as to what type of conditions formed these different minerals. When we start looking at metamorphic rocks, one of the different ways that we can form these metamorphic rocks is we can really heat up these rocks. And a classic example of this is if we had a pluton or a blob of magma that's going to heat up the rocks around it. And as a result, you're going to end up with the rocks that are real close to that magma almost melted, really, really high temperature or high grade. If we start moving further and further away from that blob of magma, we would end up with lower and lower and lower grade. And eventually you'd end up with non-metamorphic rocks. You'd end up with whatever the existing rock is, or we call that the country rock. In many cases, it is bedrock. Another way that we can form metamorphic rocks is through regional metamorphism, also called dinothermal metamorphism. And this is where we have this occurs typically at plate boundaries, at convergent plate boundaries, where you have these rocks getting pushed together and actually causing these rocks to get smushed and smashed. And this occurs at convergent plate boundaries. And these are large swaths of these metamorphic rocks. A classic example of this would be at the Appalachian Mountains, where we end up with looking at these Appalachian Mountains being smashed together, this regional stress. And then we can actually see the direction in which that stress was applied. We can cause metamorphism at convergent plate boundaries, but also at the subduction zones, where that pressure is increasing and these rocks are getting squeezed together at this subduction zone. So we can have varying amounts of pressures and temperatures occurring, all associated with the convergent plate boundaries, whether you're dealing with continental, where you end up with two continents compressing, or at subduction zones. So if we start looking at these continents are made up over a long periods of time of convergent plate boundaries, which any of the lighter, less dense, felsic rich rocks are going to not get subducted again. And so over time, these blobs of metamorphic rocks are going to get larger and larger and larger. And these are going to create things called shields, continental shields. And as I've already mentioned, ocean rocks are always getting destroyed. And so if you're building up more and more of these continents, these continental shields are going to get larger and larger. Now, in the chapter on plate tectonics, we talked about Pangea. Now, there have been supercontinents before Pangea. They looked a lot different because we didn't have as much material being added onto the continental shields. As we are constantly causing more subduction taking place, these continental shields are getting larger and larger and larger. And we're separating out the continental felsic-rich rocks from any of the rocks that are being subducted, which have a higher iron concentration or more mafic. And so when we start looking at this map of the world, we can see that a lot of these continental rocks are these large continental shields. We have these cratonic platforms, which are basically exposures of sedimentary rocks, with the exception of I put in a little couple of dots here in the St. Francis Mountains, but we're surrounded here in Missouri by this cratonic platform, which means that we probably have a lot more of this Precambrian shield beneath this, but we have a bunch of sedimentary rocks on top of us in this area. But if we start moving to the west coast of the United States, we have younger mountain ranges, which haven't been fully attached to this shield, and so we end up with some more faulting in those regions. So at this point, we've looked at all three different types of rocks. We've looked at igneous rocks, we've looked at sedimentary rocks in the last two chapters, and this chapter we've looked at metamorphic rocks. And you can take any existing rock and turn it into a different rock. So you can take an igneous rock and you can break it down into sediments and find sedimentary rocks. Some examples around here would be places like Pickle Springs, where you have igneous rocks of the St. Francis Mountains that have washed down and formed some sedimentary rocks in Pickle Springs. Now, the metamorphic rocks around here are virtually non-existent. We do have the St. Francis Mountains, but the rocks around here, all of our metamorphic rocks have pretty much all washed away. Hawn State Park has just a couple of little exposures of these metamorphic rocks that are there, but most of our metamorphic rocks surrounded the blobs of magma that entered in, and the lava that formed these volcanic materials have all washed away. And we're covered by a lot of this sedimentary rocks in this area. So here in Missouri, we don't really have too much metamorphic rocks because all of our metamorphic rocks have washed away to form new sedimentary rocks. But you could take a metamorphic rock or a metamorphic rock or a sedimentary rock, and you can melt them both to create these metamorphic or igneous rocks again. So there's a great description or a video in the student site that makes reference to this rock cycle and how you can take one rock and turn it into any of the other two major rock categories. I'm sure a lot of you have already heard this in younger schools, talking about the different three major rock types, but hopefully in the last three chapters, you've been able to look at these a little bit more intensely, a little bit higher level of depth. So when we start looking at these different rock types, we have blobs of magma, which are going to have these interlocking grains. If we look under a microscope, you would see even that the extrusive igneous rocks have these tight grains, giving it a much more homogeneous texture. If we start looking at the intrusive igneous rocks, you can see those individual large grains. The sedimentary rocks are easy to identify as these nice horizontal layers or beds. And again, we can look at the clastic versus the non-clastic, looking at the ingredients of those materials or what those grains are made of. And then we have metamorphic rocks. Now, a lot of the metamorphic rocks are going to be those regional metamorphic rocks that are going to have that foliated texture because we're causing more pressure in one direction than the other. We do have the non-foliated metamorphic rocks, which are a little bit more difficult to identify, but fortunately here in Missouri, we don't have to worry about those. So at the end of this chapter, I said I was going to do something a little bit more, a little bit different. One of the things that we're going to be looking at is how do you get a metamorphic rock to turn into a different structure? And again, in the lecture, I mentioned graphite turning into diamond. How can you change a one mineral into a different mineral with a different crystalline structure? And I use the example diamonds and graphite. So if you don't know what that is, go back and listen to this lecture again. If we start looking at this, the next question is, which of the following metamorphic processes which change the shape and size of the grains, but without changing its chemical composition? Takes little grains and turn them into bigger grains. The next one is looking at which of the following metamorphic conditions applied to rock leads to solid state diffusion. Diffusion is when you're taking two rocks and you're pushing them up against one another and you're moving around really quickly and you break one grain off and move it to a different area. So what would increase this? Here's your hint on this one. Other hints would be looking on section 6.2, page 171. Another change that is going to, what terms is used for the compositional change that takes place during metamorphism, where we're taking material and you're heating it up and you're mixing this material. You're mixing these materials, and so you, I stumbled over the word a number of different times. So I'm not going to tell you what it is, but you may want to go back and see me stumble over those words again. What type of foliation is produced by altering light and dark layers of materials? And here's an example of these light and dark minerals. We call this that answer. Here's an example of a non-foliated metamorphic rock. And so if we start looking at non-foliated metamorphic rocks, some of these answers, options here are not metamorphic rocks. So make sure you're looking at a metamorphic rock. I know I've mentioned marble a couple of times in this lecture. So if we start looking at this marble, what is the protolith? What was the type of rock that became this marble? So in this image, it's a fairly common occurrence to try to list from lowest grade to highest grade, and you're going to get different types of rocks. So what is going to increase the pressure? What is the lowest temperature and pressure to the highest temperature and pressure conditions? When we start looking at regional metamorphism or dinothermal metamorphism, what type of conditions are going to cause these regional metamorphism? And so I mentioned the Appalachian Mountains, and you can actually see which directions where North America and some other continent over here on the other side of the Atlantic Ocean crashed into the metamorphic to create these metamorphic rocks. So the next question is looking at the different pathways a rock can take. Don't forget about those shortcuts, but which one of these can occur? Foliation tends to occur again during what type of metamorphism? When rocks get pulled apart, get smashed together more in one direction than the other. If we add fluids, or if we heat up that rock and cause contact or thermal metamorphism. So where are you most likely to find a lot of metamorphic rocks? Look at these different conditions and try to find one of these that we actually talked about in this chapter. So with that, here's one of the last questions in this chapter. If you are near a volcano, what type of metamorphism would you expect to find? Shale is likely to metamorphose. If we were to just slightly take shale and add a little bit more heat or pressure, usually pressure associated with this one, what's going to happen to that shale? Is it going to stay as shale, or is it going to turn into one of these four options? The next protolith, if we heat it up even or squeeze it even more, don't worry about that. But what is the next phase in that option? So if you have any questions, send me an email. And send me an email if you liked this presentation a little bit better, the modifications that I put in here.